Hello, so today we are going to continue on this problem, which is part of Leetcode context 304. So the problem says that we have, it's find closest node to given two nodes. So what's being asked here is that we have a directed graph. We have n nodes numbered from 0 to n minus 1. And each node has at most one outgoing edge, right? And then the graph is represented with the zero indexed array of 4 edges, where basically there is an edge from node I to edges of I. And if there is no outgoing edge from I, then we will denote that with -1. And so we get two nodes, node 1 and node 2, and the goal is to return the index of the node that we can reach from both node 1 and node 2, with the condition that the maximum between the distance from node 1 to this node, let's call it node I, so the maximum between the distance from node 1 to I and from node 2 to I is minimized. So we want to get a node that can be reachable from node 1 and node 2, but at the same time the maximum distance from node 1 to I and from node 2 to I is minimized, right? And if there are multiple answers, we want to return the smallest index, and if there is no answer, we want to return -1. So let's take a look at an example to understand here. So we have, this is a representation of the graph denoted by this. So you can see here 0 and here 1, 2. So basically the indices, and here 3. So we have an edge from 0 to 2, that's represented here. We have an edge from 1 to 2, from 0 to 2, that's represented here. From 1 to 2 is represented here. From 2 to 3 represented here, and then we have 3 has 0 outgoing edges, so that's why it's -1, and so that's why it doesn't have any outgoing edges. Now, what's the index of the node reachable from both 0 and 2, where the max distance from both of these nodes to this node I is minimized. While that node is actually 2, because from node 2 to 2, then the distance is 0, and from node 0, I forgot, the node 2 is 1. So from node 0 to 2, distance is 1. From node 1 to 2, distance is 1, right? So the minimum, so the distance is 1, right? If you try 3, well, 3 is reachable with 2 for each one of them, so that's not the minimum, and so that's why we pick 2 here, node 2, and return node 2. So that's the main idea of the problem. Now let's see how we can solve it. Okay, so let's see how we can solve this problem. Now, the main thing we can do here, so this is the example that we had, 0 and 3, right? So the main thing we can think about is, well, what we want is to minimize the distance, right, from node 1 to I and node 2 to I, and this we would want to take the max, but we want to minimize this distance, right? And so what we can do is just calculate all distances. So calculate all distances from node I, from node 1 to all i's, right? And then do the same thing from node 2 to all nodes, to all other nodes. And then once we get this, just go through every node, so for all i's, basically compare the distance, right? Compare the distance from node, take the distance from node 1 to I, and distance from node 2 to I. Take the max of that, right? And then once you take the max of that, just compare it against the other i's. If it's smaller than smaller than the one, the best one we've seen so far, then update the best one we've seen so far. If it's not, then leave it, and then at the end just return the best we've seen so far, right? And what I mean by best so far is just the best distance, right? The best of the maximum distance from node 1 to I and from node 2 to I. So this is actually just a direct translation of the problem. We want the minimum of the maximum distance between node 1 and I, node 2 and I, for all the nodes I reachable from both, right? So here we need to make sure also reachable, we need to make sure I is actually reachable from node 1 and node 2. Okay, and then we can just take the best as we are traversing all the nodes I, right? So that's the main idea. Now this here should be straightforward to do, but how do we calculate all distances? Well, to do that we can just use DFS or BFS, right? So we could use, for example, DFS and just update the distance once, and that would be its minimum distance, and then once we reach it and get its distance, that's pretty much it. And we can just use the same function actually to get the distances for node 1 and the distances for node 2. So let's just see how we can write that function. So let's call it DFS. So node, to generalize, we will pass either node 1 or node 2, and the distance so far, the node that we reached so far, and this would be just the array of nodes, array basically for where distance of I would be, let's call it distance 1 of I would be the min distance, right, from node 1 to I, and we can have just 2I to be the min distance from node 2 to I, right? And so the function needs to be generic to keep the distance here. Now we know that if a node has node outgoing edges, we will get the value -1, so we will need to safeguard against that. So if the node is different than -1, so it's a valid node, and we haven't yet filled the distance for that node, so let's call it different than -1. So this would mean that we'll initialize all the distances with -1. If this is the case, that means we can visit the node. So first we will need to set its distance to be equal to this d. This is just computing at each level of the DFS. We'll increase it by 1. And so in our we will call DFS on the neighbor. What's the neighbor? We know that edges array, right, of node, that's the node that's the node that node points to, right? And so we can just pass that. So that's the only neighbor here. And then we want to increase the distance because now we are 1 level deep in our DFS. So d plus 1, and then we can pass this array of just as is. So this is the DFS function, and then we can just call this DFS function for node 1 and node 2. And then after that, we can do this last step where for every node, we will if the node is if the node is reachable from node 1 and node 2, we will just check the max of the distance from node 1 to that I and node 2 to that I, take the max and see if it's the best we've seen so far, which means it's the min compared to what we've seen so far. If it is, update. If not, leave it, and then at the end we return the best so far. Yeah, so that's pretty much it. Now let's write this in fully and make sure it passes test cases. Okay, so now let's write the code here. So what we need is, as we said, we need first to have the length of the edges. And then we need to have 2 arrays for each node. So what this would mean, basically, let's just clarify here. So distance of 1i is the min distance from node 1 to I, and then dist2i will represent the minimum distance from node 2 to I, right? And so we'll initialize it to -1 to represent nodes that are not reachable yet. And so to do that, we'll just say -1. And since we have only n neighbors at most, we'll just have an array of size n and do a similar thing for dist2. And now let's write our DFS function. So we need node, d, and distance, right? And we need to call our DFS function here with node 1, and distance starts out as 0, and with dist1, that's for the distances from node 1 to I. And then we want to do a similar thing for node 2, right? And this would be dist2. And then here, once we have the distances, we can get the min node, or let's call it desired node, whatever it is, right? But let's first write our DFS. So we need to make sure that this is a valid node, because edges of node can be -1 if it doesn't have any outgoing edges. So in case we pass it this, which is -1, so the node that's not a valid node, we need to check against that. So only those that are different than -1. And we want the minimum distance. So with DFS, when we first update, that's the minimum distance, right? Because every time we do a DFS call, we'll increase this distance, d, right? So once we set it, we don't want to set it again, because the previous value is always the best one. And so we want to check that the distance of node is different than -1, because if it's not different, that means it's already set, it already has the minimum distance. We don't want to update it, because that will update with a bigger value. Okay, and now with this, we can update the distance for the node is equal to d, so the level we are at with the DFS. And then we want to call DFS on the neighbor of nodes. And remember that in the problem, we have basically an array of edges where there is a direct edge from node I to the node edges I. And so I here for us is node, and so it's there is an edge from that node to edges node, right? And so that's what we want to traverse next with our DFS, which is edges of node. And distance is the next level. We'll do distance +1, and then we will pass the same array distance, right? So that's our DFS. Now here we want to have first the best distance, right? We'll initialize it initially to float of infinity, because we are picking the minimum one, and so we'll start with the highest value possible, so that if we compare against anything else, it will get updated. And then what we actually want to return is the common node that has this best distance, right? So let's start with -1, because if we don't find it, we want to return -1. That's what the problem says here, right? Okay, so now that we have that, we want to go through for every node, so for every I, we want to first check that node is reachable that I is reachable from node 1. So what does that mean? It's reachable if the distance of 1 to I is actually different than -1, because if it's equal to -1, that means we were never able to reach it and update this, right? From node 1 here. And so if it's different than -1, that means it's reachable, and distance to I is different than -1. So basically what this would mean is I is reachable from both node 1 and node 2, okay? If that's the case, then we want to check if it's the best distance we've had so far. So if best distance is bigger, so if it's not actually the best one we have, so it's bigger than the max of the distances from node 1 to I and node 2 to I, if it's bigger, then we want to update it with this new best one, right? But at the same time, we want to update the common node here to I because we found a better answer, and so we need to update it. The answer is actually the node. And then at the end, we want to return common node. Okay, so let's run this. Yeah, so sorry, there is one mistake here. This should be different than -1, similar to here, because we want the nodes that are, we want to make sure that I is reachable from both node 1 and node 2. And reachable means different than -1. The other thing here, the other error here is that we are checking if distance of node is different than -1, which means we have already set it, right? And so that won't be the minimum because we'll update. What we want is actually equal to -1, which means we haven't visited it yet, and so we haven't assigned any distance to it. So that's what we want here. Now let's run this after fixing those. Okay, and let's submit. And that passes test cases. Yeah, so that's pretty much it. Now, in terms of time complexity, DFS is of E plus V, right? E being the number of edges and V being the number of vertices. The number of edges is N. The number of vertices is also N. So here we have 2N, so just N. We are doing 2 DFS, and then we are doing 1 loop of N, right? So 2N plus N overall of N time. So over time here, in terms of complexity, we have these 2 arrays, so oven as well. So oven time, oven space. Yeah, so that's pretty much it for this problem. Please like and subscribe, and see you on the next one. Bye.